Welcome to Geek Do-It-Yourself Mechanic. The purpose of this video is to discuss computer-controlled systems. Obviously, I'm going to give a very high-level overview. The reason I find this topic important is many times when I'm trying to explain a trouble code or how modern cars work, it always ends up boiling down to having to explain computer-controlled systems. What does open loop mean? Closed loop? Actuator, sensor. Why do modern cars need that? The old cars didn't. They just used a carburetor. Anyway, the computer control systems use sensors to emulate what the old mechanical systems did. So let's go through that. Hopefully I'll be able to explain that to you, get you a good high-level understanding. So navigate to Knowledge, Control Systems. And I have a very simple control system here modeled. It's using JavaScript, so don't expect anything spectacular, but I did implement it in a way that would help us understand how the car computer control system works. Let's go over the overview. So the purpose of this controller is to model a bucket with a hole in the bottom and a water spigot at the top. In addition, it tries to keep the bucket half full. So again, you have a spigot at the top, which is like an actuator. The bucket is the system you're trying to control, and then the controller is tuned to match that the spigot input, as much water is flowing in, is flowing out. What that means is what a controller is trying to do is get the system in harmony, in a steady state. Well, let's go a little more about what a controller is all about. So these are the topics. Usually when I'm explaining control systems, these topics come up. I'm going to sort of do them out of order with hopes of explaining, because no matter where you start, you end up chasing your tail. So let's go over the diagram, since they say pictures are worth 1,000 words. So the system is the very thing you're controlling. So in this example, it's the bucket. But in your car, it could be the engine, the brakes, the transmission, a system that you're controlling. That system always has sensors: mass air sensor, temperature sensor. And then the controller is like the PCM, ECU. It has so many terms. But it's the main computer that's controlling the car. When you plug your scan tool in, that's what you're communicating with. Or the numerous controllers of your car that communicate together. But let's stay simple. You have the one controller, the PCM. And then it has actuators. Idle bypass valve, injectors, things like that to change the behavior of the system. But the system also has external stimulus. That would be you, is one of those stimuluses. You press the gas pedal. You hit the brake. The temperature. So a car control system is extremely complicated. So again, I am not saying the controller I emulated here is anything to the magnitude of your car. It was implemented to just allow this discussion to be discussed and give examples. And then lastly is response. That's the response to the actuator and the stimulus together. For example, in your engine, you press the gas pedal and it's trying to idle, but you're trying to raise the RPM, so the response is higher RPM. The sensor would read that, it would make appropriate calculations, give input, plus the stimulus, and the system goes. But let's pretend you're just cruising down the freeway, you're in cruise control, That would be considered steady state. Nothing's really changing much. The temperature's not really changing much. You're not touching the gas pedal. That would be steady state. So again, the controller is the main device that's trying to control the system. ECU, PCM. A sensor. That's a device used to monitor the system to get important metrics of that system. Could be temperature. In our case, it's the level of the bucket. An actuator. That's something that acts on the system. In our case, it's the spigot. But it could be a relay, fuel injector, whatever. This is an interesting topic. Let's go back to this diagram. So when I discussed my previous example, notice I started at sensors as input. Because sensors are being used by the controller, this is called closed loop. Because it's using what the current state of the system is to adjust its behavior. Is the engine speeding up, slowing down, and where do I want to go? Is it higher RPM than I want to be? Is it lower RPM? That changes what you're going to do, right? So that again, that's closed loop. Closed loop again is when the sensors are used to determine how to control the system. Open loop is when it is not. Obviously, the controller does its best job when it can sense the system. For example, I'm sure you could get very close to your shower temperature just because you're used to where the dials are. But if you wanted to be precise, you would use a temperature sensor. But usually we don't, right? Because what do? We get in the shower, we set it, and we adjust it. Look at yourself. Go in there, you set it up, you let it warm up, and I guarantee you'll change it. Well, you just went into closed loop. You first went into open loop because you turned on the shower, you let it warm up, you come in, and then you change it. That's closed loop because that water's hitting you. You're the sensor. So again, open loop is when no input is being used. How that relates to a car is your fuel system is in open loop until your O2 sensors warm up. When they're warm is when they can sense the air fuel or the amount of oxygen, or the modern air fuel sensors can detect the air fuel ratio in the exhaust gas to tell the computer so it can adjust. But that's beyond the scope of this discussion. I just wanted to give an example why I need to discuss open loop in cars. Long-term trim and short-term trim. This is commonly used in automobiles. When I've written other controllers, I didn't use this technique. But I wanted to implement it in this one because that's used in cars. So long-term tends to be stored in flash or is remembered. If you don't know what that is, it's just remembered when you restart the computer. It's like writing it to your hard drive, quote unquote. And those are macro settings, changes. So when you went into your shower and you turn those dials, that would be considered long-term trim because you remember where those water gauges should be. Short-term is the immediate. When you get in, you're making changes. So if you had a thermostat in there, or thermometer, and you would, let's say you wanted a specific temperature and the room happens to be changing because of air conditioning, you'd be constantly slightly changing those dials to keep it in there. Well, the car does that a lot, and you'll see in this controller it does that too. Again, long term are macro settings, the short term are little fine-tuning settings. Let's talk about the controller now. Okay, what's going on? Let's go through what is being displayed. You have the long-term trim, short-term trim. This is the inflow. This represents how much the spigot is letting water in. The drain rate represents the hole at the bottom. This lets me change the drain rate. Because right now the system is in steady state, as you can tell. Everything is nice and consistent. This is the sensed level of the bucket, the water in the bucket. And then these are like idiot lights. I thought I would do it as idiot lights since we're talking about automobiles. So when the bucket is empty, this goes to true, and it's in its idiot light state. It turns red. And is overflowing is the opposite. When the bucket's overflowing, this will turn to true. And this allows me to change from open loop to closed loop. We'll go into that in a little bit. So right now the system is in steady state. So if I go to open loop right now, I don't really need to know my sensors. I don't need that value because it's in steady state. But what do you notice? It is increasing the level because it can't adjust. It can't keep it at 5 in the middle because it's not using the sense values. And immediately it's adjusting, bounce down. They call this oscillation. Because you see this level oscillate up and down and then settle in. That's typical of a computer controller. Obviously, the more advanced controllers, like if we were building a controller to navigate a missile to hit a target, its computer control system, its reactions have to be very quick. The oscillation time to get back on track must be very quick because they're going at a high rate of speed. But we're just filling a bucket here, and I'm giving an example. Okay, so let's see what happens when I change to 0.1, meaning now I'm actually plugging the hole at the bottom, so I'm going to drain less. Let's see what happens. So the drain now is at 0.1. Notice immediately the bucket is going to fill up quicker, right? And let's see what the controller does. How does it change? Notice the long term now is getting involved because that's a macro change. I'm changing a lot. What this controller is modeled to try to keep the short term between positive 35 and negative 35. That allows the short term much freedom to adjust. Oh, we're starting to level out. Notice that? We're starting to get around 5. We're oscillating around 5. So now it appears the controller's in steady state. Yeah, it looks pretty good. Well, we have this little hole at the bottom, right? Let's really cause this system to go haywire and put a big hole at the bottom. And what happens? Drained it so fast. Let's see how it compensates. Clearly we need to add more water, so we're expecting the inflow to increase over 2 because we want to raise the water to 5, and then when it reaches 5 the inflow should match the drain rate, right? If you think about how you would do it yourself, that's what you would do. So right now you'd have it full blast the spigot. Says your brain reacts a little faster in this demo. Besides, I slowed it down so we can see how a controller would behave to make up for this hole, huge hole at the bottom of the bucket. Notice it just matched. Now it's increasing, and the level of the bucket, water starting to rise. Now it's going to overcompensate because now it went above, and it should slowly start to get in a steady state. And it is. Look at the inflow. It's matching 2 to drain rate of 2, and we're at 5. It's in steady state. So we'll go back to 1, what the system is tuned for. And notice how long-term and short-term are not at 0. Let's see what happens when we go back to what the system was tuned to be at. What do we notice about long-term and short-term? If you're observant, you'll remember how we started this demo. Let's see what happens. Clearly we see long-term dropping, and short-term is trying to remove water. We're almost at the same inflow and drain rate, but long-term is still dropping down. Still dropping. But yet, We're the level is where we want. Interesting. But it's dropping. That's an indication the system is doing something. In this case, it's healing itself. It's getting back to its known state. It's tuned to be at a specific setting. It was tuned. Remember I said up front, this controller was modeled that the inflow is 1 and the drain rate is 1. So let's see what happens when it finally gets to steady state, meaning long-term and short-term are consistent and the sense level are consistent. What's gonna happen? We're almost there. We're at 5. Still dropping. Well, let's see if long term goes negative. Well, with no surprise, if you remember when you started the video, long term was at 0. That's because, again, there shouldn't be any macro settings required for the controller because it was designed to be at 1 to 1 when the level is at 5. So long-term and short-term values in a car or in this demo can be used to tell if the controller is making up for something. Remember, the engineers modeled the controller for specific behavior of the system given a stimulus. And when it doesn't match what they engineered it and mega tested it, you'll see those change. So when you look on your scan tool and you see long term either positive or negative, something is up. That's beyond the scope of this discussion. In future discussions we'll talk about it, or go to Scanner Danner or Schrodinger's box. Schrodinger's cat, excuse me. They'll really go into this. Long-term and short-term fuel trim is a great discussion of this. I'll actually include the link on this page. Those are great discussions of how this concept relates to cars. Again, most of the time the car is in closed loop. The controller wants to get the system in a well-known steady state based on stimuluses, your foot, temperature changes, altitude changes, leak. The controller senses that via sensors, makes appropriate changes in actuators, and the system responds. In essence, I just gave a very, very high-level overview of computer control systems, the concept. I hope this will help you understand how automobile PCUs, ECUs function. The thing to understand is long-term and short-term. In regards to a car, those have to do with long-term fuel trim and short-term fuel trim. Those two help you diagnose many issues in the car. Again, if you see them, either one of them, way out of whack, in a car, it's plus or minus 10%. In other words, if they're in the plus or minus 10% range, that's okay. If it's outside of that, it's showing you there's an error. So, real quick, the reason why they have short-term and long-term fuel trims, especially short-term, it helps. As the car ages, obviously the sensors aren't going to be as accurate. So short-term and long-term fuel trims can make up for those and still make the car very reliable and drive great and still be clean at the exhaust. So that's why these can't be constant values. This is a way that allows it to adjust. I can take it back to the analogy of your going into the shower. Let's pretend someone upstairs has used a lot of hot water. Your settings would have to be different. In addition, different times of year, if it's winter, you might like it a little warmer, and in the summer you might want it a little colder. Well, those are minor changes based on the stimulus, right, which would be the outside temperature, how you change your computer control system. But even though there's mega changes like that, the system is still okay, right? It's not out of whack. Anyway, this concludes the discussion to simple computer controllers. Thank you for watching. I hope you found the information helpful.